This SBIR Phase 2 project, packaged mid-infrared non-mechanical beam steerer, is sponsored by the U.S. Navy with the topic number N68335 and the contract number N68335-23-C-0235. The performing team includes prime performer of Kent Optronics. Our company, Kent Optronics, is focused on developing electro-optical solutions using liquid crystal technology, optics, and advanced fabrication techniques for research and development, for prototyping and products. Kent Optronics' home facility is in New York and has a tracking record of more than 20 years with a team specializing in liquid crystals, missile warning systems, aero-optics, and radiometry. We have many commercialized products such as multispectral IR displays, switchable mirrors, switchable spectacle, tunable filters, laser protection device, large-screen LCD, night vision goggle, etc. In addition, the company has published patents and trade secrets which are issued in liquid crystal, switchable mirrors, tunable filters, night vision goggle, scene projection displays, etc. We are proud of our SBIR history and achievements. Since we obtained the first SBIR funding from the Air Force in the year 2000, we have secured many SBIR and STTR programs from DoD, NASA, NSF, and almost all of the company products and technology IPs are resulting from SBIR and STTRs. The key resources of the company include a 5,000 square foot Class 100 clean room hosting the liquid crystal device for switchable mirrors, tunable filters, and the like, a fabrication pilot line, a fully equipped optics laboratory and scene projection display assembly line, a photolithography laboratory for patterning and microfabrication, an electronics lab, and a machine shop. Currently, the company has active contracts with the Navy, Missile Defense Agency, Army, Air Force, Apple, Toyota, Samsung, etc., and has proven commercialization and transition success with over $20 million in accumulated sales revenue. We have established heavyweight partners such as Naval Research Lab, Apple, Boeing, Toyota, and the University of Central Florida. In this topic, the Navy needs a packaged, high-throughput, non-mechanical beam steering or non-mechanical beam steerer device that is able to maintain stable operation with multiple wavelength laser sources in the mid-wave infrared or MWIR band with wide steering angular range, fast speed, high beam quality, and high efficiency to deliver high laser power on target. The RT&L focus areas are general warfighting requirements, and the technology areas are air platforms, battlespace environments, and weapons. The expected specifications of the non-mechanical beam steerer device are the following: spectrum coverage, 2 to 5 micrometers, point-to-point steering speed, 1 kHz threshold requirement, angular steering range, 15 degrees horizontal and 2 degrees vertical, angular steering accuracy, 1 microradian, throughput, 30% threshold requirement. Laser power on target, greater than 1 watt threshold requirement, greater than 10 W degrees objective requirement, beam quality, M squared less than 5 threshold requirement, M squared less than 1.5 objective requirement. Optical aperture, 2 millimeters. Threshold requirement, 1 centimeter objective requirement. Beam acceptance angle, greater than or equal to 0.2 degrees FWHM, total packaged non-mechanical beam steerer volume, less than 50 cubic centimeters. Threshold requirement, less than 10 cubic centimeters. Objective requirement, electrical power consumption, less than 10 watts threshold requirement, less than 1 watt objective requirement. Operation temperature, 20 degrees centigrade to greater than or equal to 55 degrees centigrade. TRL, greater than or equal to 6, at the conclusion of Phase 2, TRL 8 or 9 in 1 or 2 years after the completion of Phase 2, MRL, greater than or equal to 5 after the completion of Phase 2, MRL greater than 7, 1 or 2 years after the completion of Phase 2. To date, refractive non-mechanical beam steerer devices have primarily been developed in the shortwave and near-infrared bands. This topic asks to develop a robustly packaged refractive MWIR non-mechanical beam steerer product with technology readiness level 8 or 9 that can be mass-produced with manufacturing readiness level 5 to 7 for countermeasures and free space optical communication. Primary organizations include the Naval Air Warfare Center Aircraft Division in Patuxent River, Maryland, who is the current SBIR sponsor. Secondary benefactors include directed energy weapons, or DEW systems, counter-drone systems, remote sensing and surveillance, communication systems, aircraft and naval platforms, and unmanned systems. The packaged MWIR non-mechanical beam steerer device has significantly improved throughput efficiency, which is greater than 30%, and wide steering angles, 15 degrees by 2 degrees, with small footprint, which is less than 50 cubic centimeters, capable of working with multiple tunable wavelength laser sources in MWIR. Now let's discuss the key messages on this slide. The performing team is developing the MWIR non-mechanical beam steering device under the current SBIR Phase 2. The non-mechanical beam steerer device is capable of continuously steering a MWIR laser beam across the field of regard without blind spots. The MWIR non-mechanical beam steerer product exhibits characteristics of large acceptance aperture of up to 1 centimeter, small footprint which is less than 50 cubic centimeters, fast response rate around 1 kilohertz, wide steering angles which is 15 degrees by 2 degrees, high throughput efficiency which is greater than 30%, high beam quality which is m squared less than 5, and power on target which is greater than 1 watt. The team has developed the key technologies as follows. 1. We have developed new designs of shortened waveguide to improve the throughput efficiency using environmentally friendly materials. 2. Our passive waveguide chip is under manufacture process. 3. We have utilized a new LC with larger birefringence to increase the steering angles and efficiency. 4. We have applied an angular amplifier telescope with proper amplification ratio to boost the steering angles. 5. We have used a photo alignment layer to minimize the LC absorption and scattering loss to further increase the throughput efficiency. 6. We have designed a telescope system to accommodate laser sources with large beam sizes. 7. Our manufacturing line for mass production is in progress. Our contract for this topic is currently in Phase 2 SBIR with processing environmentally friendly materials for waveguide thin film deposition with technology readiness level 6, aiming at 8 or 9. The initial implementation was planned for chalcogenide glass, which is less environmentally friendly, used for the waveguide core and subcladding layers. We are seeking follow-on funding for mass production using environment-friendly materials. This fits into the program of record which has been laid out with the NAVAIR POC. New technology developments have been and will be carried out in waveguide chip deposition, LC assembly, light coupling, whole device packaging, etc. In order to meet the Navy challenge, we have performed the following key activities. First, increased throughput efficiency using low-loss liquid crystal, shortened waveguide chip and photo alignment layer. Second, larger steering angles, applying AAT and new LC with large birefringence. Third, large aperture size, using appropriate telescope to shrink the size of incident laser beams. Fourth, acceptance of multi-line lasers enhance the functional flexibility of the non-mechanical beam steerer device. Specifically, compared with the current baseline, the features listed in the reference, the non-mechanical beam steerer device developed under this topic has the following advantages. 1. We have increased throughput efficiency from the baseline of 3% to 30%, which is 10 times higher. 2. The out-of-plane steering angle is increased from the baseline of 0.6 degrees to 2 degrees, which is greater than 3 times larger. 3. The in-plane steering angle is increased from the baseline of 14 degrees to 15 degrees. 4. The aperture size is increased from the baseline of 2 millimeters to 1 centimeter, which is 5 times bigger. 5. The acceptance of multiple tunable wavelength laser sources in MWIR enables the device to be flexible in coupling free space and fiber-coupled lasers. The following will be conducted as the topic transitions beyond Phase 2. 1. We will conduct comprehensive prototype device testing and demonstrations to meet all the specification requirements with the Navy sponsor. 2. Our non-mechanical beam steerer device development is ahead of the program of record schedule, potentially accelerating funding allocation and deployment timelines. The primary transition includes the following. 1. Perform final testing of the packaged non-mechanical beam steerer device in a relevant environment. 2. Carry out integration as applicable to the specific Navy platform. 3. Transition and integrate to an airborne platform of interest chosen in consultation with PMA 272. In addition, the main technical objectives beyond Phase 2 will be the following. 1. We will convert the non-mechanical beam steerer prototype into our beta production version. 2. We will fabricate 5 non-mechanical beam steerer beta version products. 3. We will conduct field and flight tests. 4. We will deliver and integrate the beta version non-mechanical beam steerer product into the Navy laser delivery system. 5. We will advance the roadmap leading to manufacturing readiness level 7. The commercial uses and opportunities of this topic are as follows. 1. This technology is beneficial for free space optical communication, medical diagnostics, chemical sensing, and other applications that utilize mid-infrared spectroscopy. 2. Non-mechanical beam steering has LiDAR applications at MWIR wavelengths. The non-mechanical beam steerer device can be applied to various systems from DoD, Navy, and commercial sector, which include but are not limited to the following. 1. Directed energy weapon systems, or DEW. We will enhance the performance and precision of DEW systems, enabling more accurate targeting and engagement of threats. 2. Counter-drone systems. MWIR lasers are often used in counter-drone systems for detecting and neutralizing hostile drones. Non-mechanical beam steerer could improve the agility and effectiveness of these systems. 3. Remote sensing and surveillance. Laser-based remote sensing and surveillance platforms, such as those used for maritime or border security, could benefit from non-mechanical beam steerer technology to enhance their capabilities in detecting and tracking targets. 4. Communication systems. Laser communication systems are becoming increasingly important for secure and high-bandwidth communication in military networks. Non-mechanical beam steerer technology could improve the efficiency and reliability of laser communication links. 5. Aircraft and naval platforms. MWIR lasers are used in various aircraft-mounted and naval-mounted systems for targeting, tracking, and defensive purposes. Non-mechanical beam steerer technology could enhance the performance of these systems. 6. Unmanned systems. Unmanned aerial vehicles, unmanned surface vessels, and unmanned underwater vehicles equipped with laser systems could benefit from non-mechanical beam steerer technology to improve their capabilities in reconnaissance, surveillance, and targeting. The non-mechanical beam steerer is intended to be transitioned and integrated into the Navy's laser delivery systems. We can also sell non-mechanical beam steerer products or license the technology to the prime contractors and commercial laser-guided system integrators. The primary transition needs to integrate the non-mechanical beam steerer device to an airborne platform. The secondary transition paths include our military agencies, including the Navy, Army, Air Force, and other defense organizations with the need of beam steering. Another secondary transition path with industry agencies, including prime defense contractors such as Boeing, Lockheed Martin, and Raytheon, commercial aerospace companies such as Boeing and Northrop Grumman, and automotive industry leaders. The prime's verticals and superior integration will take advantages of the non-mechanical beam steerer device features, such as small footprint, fast response rate, wide steering angles, high throughput efficiency, high beam quality, and power on target. The non-mechanical beam steerer integration offers prime contractors verticals with multiple advantages, ultimately leading to benefits such as enhanced reliability, versatility, compactness, agility, precision, efficiency, effectiveness, and power delivery in laser applications. The following is our contact information. We are Kent Optronics Incorporated. Our primary point of contact is Lei Li, our President and CEO. His phone number and email are shown on the slide. Please come and visit us at 40 Corporate Park Road in Hopewell Junction, New York. Let's discuss how MWIR non-mechanical beam steering may assist your company or organization. We may coordinate through our Navy sponsor for a demonstration of the non-mechanical beam steerer device's beam steering capability, showcasing your application in enhancing reliability, versatility, compactness, agility, precision, efficiency, effectiveness, and power delivery in laser applications.